We're going to go into the next principle, which is an area of synthetic organic chemistry that most undergraduate folks don't really talk about. And it's usually something that you pick up in a graduate level course. And it is a very specialized topic, but it's an important one. It's another tool in the synthetic chemist's arsenal. And it's not used in every synthetic scheme, but it's used in a lot. So hopefully you'll come away with a better understanding about derivatization and protection, deprotection strategies. Show of hands, how many people have learned about protection, deprotection, and in synthetic organic? Oh, a lot more than I thought. Good. All right. So synthetic routes and derivatization and chirality, that's really where it's used tremendously, is in creating chiral molecules, particularly in pharma. So unnecessary derivatization is really loaded because it kind of gives you the idea that it isn't necessary all the time. That means that you really have to think about how you're going to approach your synthetic steps, because we end up with a lot of functionalities that we can't use in the molecule right away, and we want to save and not have them reacted at a certain point in the strategy. So again, design is a critical part of this. Since most of you know why it's used in chiral resolutions, hopefully I won't be too repetitive. So it's a disclaimer here. This is highly specialized, I think. Synthetic organic chemists do this a lot over time. It's something that you get an intuitive sense about, and it's really in the total synthesis of natural products and complex molecules. It's used a lot. It's a skill, though, and like any skill, it's something that you can learn and get better at. So, you know, it's not as though you can't learn how to do it and do it well. So like this quote, no single correct route, however, some will be obviously better than others. I think this is an area that is going to eventually undergo a lot of change, because as we computerize and automate more, the ability to do retrosynthetic analysis is going to actually become a reality. And so the necessity of becoming encyclopedic with named reactions and that intuitive sense, I think, is going to grow less with time, because computers are a lot more sophisticated. They can hold 8 million reactions in memory, whereas most synthetic organic chemists can't do that. So the idea is that we need to come up with ways to synthesize molecules from a lot of different directions. So this is just a standard molecule, not anything special. It gives you an idea of how it might be built. There's lots of ways it may be built. You've got acetylenes here, which again, highly energetic molecules, and in this industry are generally not looked upon as something that we like to use, although they're used quite a bit in early medicinal chemistry, route development, and that kind of thing. They're used academically, like I said, both aziridines and acetylenes and that. Once again, we use these molecules because thermodynamically and kinetically they go very rapidly, so we like them. We can make whole libraries very quickly. So you know what a protecting group is. Basically, we're just trying to protect the molecule and ensure that the framework that we're interested is maintained at least for a step or two until we can do a different kind of chemistry on that particular functional group. So it avoids interfering with another reaction, and this idea of easy to put on and easy to take off is important. But what is the issue here is it violates the principle on atom economy, right? Where obviously if you're using a protecting group, you don't have an atom economical reaction by definition. So it's really the downfall. I won't spend, again, a lot of time, but it's just we want to react this thing, but we're afraid that particular ketone will react, where we want this end to make the alcohol, so we just protect it so we can reduce the ester to the alcohol, standard reaction, we protect it. And there are a lot of choices for how to protect it. This is just one. Again, there are whole libraries of protecting groups. So again, in our decision to protect a group, we can be better or greener in which choice we make for the protecting group. And then the overall reaction ends up with the alcohol. So these are a few examples of common protecting groups. So amino, what do you notice about these particular molecules in general, with protecting groups in general? Are they small? Are they large? They're large. They're large and bulky for a reason. That means that they won't react when we put them on the particular molecule or the functional group we want to protect. We want to make sure that the reagents, usually pretty aggressive, that we're using, like lithium aluminum hydride, won't react with that particular functional group. So they're many times sterically hindered so that the other molecule cannot get in. And again, once again, from a mass efficiency perspective, from an atom economy perspective, this is a bad strategy. Again, examples of carboxyl type protecting groups, and I just have an example of sucralose. So are you familiar with what sucralose is? Artificial sweetener, Splenda. And they start out with a sucrose molecule. It's kind of interesting. Rather than using that as a sweetener, they tritylate it, and then they detritylate it, and they chlorinate it, and then they deprotect it. So they end up with this chlorinated molecule, sucralose, which again is Splenda. Now, what can you say about that? If I didn't show you what the trityl molecule was, you might suspect that it's got some problems. But for every single sucralose molecule, how many trityl compounds do we have, or molecules? So we introduce it in basic conditions, pyridine, which is not a very happy compound itself. It's not nice to work with. It's got a lot of safety and health issues associated with it. We cleave it under rather mild conditions. And there's 3 of these types of molecules for every molecule of sucralose. So when we're talking about kilos of this stuff, again, a massive amount of waste that we're dealing with. So obviously, if there could be some other way to get that artificial sweetener, we would like to do it. So typically, these are the kinds of functionalities that are protected: alcohols, amines, aldehydes, ketones, carboxylic acids. Again, when you're building large complex molecules, pharmaceuticals, and agrochemicals, these functionalities are usually found in multiple places, and many times these kinds of functionalities are part of the chiral synthesis. And sometimes it's not always easy to tease out when actually a protection reaction is taking place because there's simultaneous reactions happening. So you get a transition state that's actually being protected. So again, I'm sure if you're practicing synthetic organic chemists, you know this. Some routes are better than others. And the trick is finding the right route. So this is, for those who don't do this, you study the molecule, you assess the topology, the bond connectivity. It's all about making and breaking bonds in the order in which you're making and breaking those bonds. You identify functional groups that either you want to maintain, protect, or put into the molecule. And this notion of strategic bond disconnections is an important one in how you're designing that molecule. Just as you want to make strategic bond connections, you can do those disconnections in a way that will help you to establish the molecule you're after. So you always are looking for your stereogenic centers. And again, we've talked a little bit about racemic mixtures and chirality and the difficulty that chirality introduces into a total synthesis of any kind of product. And stability of the overall molecule is important. So once you understand the target and you're trying to reduce the molecule to similarly sized building blocks, okay? And very early on in the second presentation, I believe it was, where we were talking about strategies of whether it's a linear synthesis or a convergent synthesis. Really, at the end of the day, from a green and a sustainability perspective and a life cycle perspective, it doesn't matter. There's a lot of people who spend a lot of time saying a convergent synthesis is better. It's really just a variation of a linear synthesis. If you go far back enough, it becomes a linear synthesis. It's just the size of the fragment that you're bringing into the overall molecule. So don't get distracted and don't get into arguments with people saying, gee, a linear is inherently less efficient than a convergent synthesis. It's nonsense. It's not the case. So again, you think about the complicated features and then talk about the oxidation states. Remember that back in the energy discussion I was saying, we many times don't pay as much attention to oxidation states and using that in the overall synthetic scheme. But that's really important, is where we choose to oxidize, where we choose, if we have to do a chiral synthesis and we have to do a chiral resolution, the order in which we do that resolution makes a lot of difference. If we do that chiral resolution as early as possible, then you ultimately will have a much more mass-efficient reaction than you will if you do it very late stage, because you build up a larger portion of the molecule. Okay? So again, if you have to do a chiral resolution, then do it as early as possible. And ideally, if we could do everything by asymmetric catalysis, that would be the way to build a molecule in terms of chirality. So again, there's lots of different ways particularly to get to that thing. We can oxidize, unmask, we can reduce or unmask. So again, this notion, there's lots of different ways to get to where you want to get to. Not all of them are going to be equally as good. Symmetry is important, and pseudosymmetry are extremely important. Multiple bond disconnections, extremely important. Bonds to heteroatoms, easily formed. And carbonyl groups, as you know, are very useful in synthetic schemes. So double bonds. Remember when we were pointing out in the renewables, one of the things that's very different about many of the natural products is they aren't as heavily conjugated molecules, right? Whereas most of the petroleum are in highly reduced state forms and lots of double bonds. So it's a lot easier synthetically to work with those kinds of molecules. We can just exploit the double bond, or in some cases triple bonds, depending. How do we avoid it? Well, if you can, you find something. If you can find a natural product that is already functionalized and isn't overly functionalized so that we end up having to reduce a lot of the carbonyl groups, then we might go that route. But again, in the current state of chemistry, that's very difficult. We just don't have that kind of set of molecules, and we don't have the chemistries that make this easy. Biotransformations, again, I've made the case, I hope, previously about synthetic biology. I think that hopefully you will begin to see synthetic biology as just another tool in the synthetic chemist's toolkit. All right, so we can construct a molecule, construct an organism. You know, you can go out and in 2 weeks get an organism genome made synthetically, and many times create what you're after. And then you can go through various things to industrialize that organism. But just to show proof of concept, it's now very simple to do. So please start considering synthetic biology as just another synthetic tool and employ biotransformations. They're highly efficient. Atom inefficient reactions are inherent to stereochemical reactions. And I'm not going to go into this since I don't have much time and since you're all pretty well practiced about chirality. We've talked about racemic mixtures, and this is really the bane of the synthetic organic chemists, again, in pharmaceuticals, and a lot of effort is being put into asymmetric catalysis to try and get away from resolutions and having to do these. And again, that's the hope of biotransformations because they're much better at getting to the molecule that you're after. We talked a little bit about classic resolutions. So hopefully you understand very important strategy. You knew that already probably. Retrosynthesis is an important design tool, and it's important that you spend a lot of time in planning how you do your synthesis. You know, spend the time on the paper or the computer or however you do it, doing the search for the particular structures or the routes that you're trying to do. Chirality is extremely important in biological senses, huge implications for life. Most chiral resolutions are very mass inefficient, so again, there are strategies for dealing with those. It's important that you use and exploit those strategies. And there are a few non-chemical approaches to separating chiral molecules, which get into chromatographic type separations and that kind of thing. So any questions?